Welcome to day 39 of 50 days of tutelage. In today's class, I'll be talking about energetics and thermochemistry. So what are we going to be discussing in this class? You see, when chemical reactions occur, it involves the breaking of bond within the reactant and formation of new bonds within the product. This process usually involves the liberation, or it always involves heat generally. There's always a transfer of heat. So heat is always probably coming in, going out, or remaining the same. There are so many things that would involve heat. So that is why we want to talk about energetics and thermochemistry. So to properly understand this, one thing that we would love to discuss is we want to discuss the kind of terminologies that we'll be using that we'll use in chemistry generally. For instance, anytime we're discussing anything in chemistry, we always say a system. So the system we are dealing with, and this system is the part of it is actually what we are concerned in that reaction. Everything that we're concerned with in that particular reaction. So for instance, if I'm considering the reaction between hydrogen gas and oxygen gas to give me water, then that implies that the system I'm actually concerned with is this hydrogen gas and oxygen gas. Now, so basically the reacting chemicals are known as the system. So the setup of the system. But this system will be in a container. So it can be in a container, it can be in a gas jar, it can be in a flask, it can be in a tube, whatever it is that it is going to be. You call them the surroundings. So these are going to be the surroundings, or we call them the immediate environment. So these are what we call surroundings. Also, the air molecule that surrounds it, and the room where you are performing the temperature, all of these things are called the surroundings. So looking at these two things, we'll be talking about the interaction between the two of them, how the surrounding affect the system and how the system affects the surroundings. And so the first thing we'll be talking about in this energetics and thermochemistry is the concept of enthalpy. The concept of enthalpy. So enthalpy is represented using theta H, enthalpy. So what is enthalpy? Enthalpy is the total heat content of a system at a constant pressure. It is the total heat content of a system at constant pressure. So if you have this system now, the total heat content that you have there, that is delta H, is called the enthalpy. So enthalpy is just another name for heat anyways, but in the case of chemistry, we regard it as heat content. If you were in physics class yesterday, I was able to discuss about quantity of heat as well using this. So enthalpy is more or less like the same thing as that as well. So but there's always the enthalpy change. Okay, sorry, I've already represented delta H as the enthalpy change. So enthalpy is H, that is the quantity of heat. But enthalpy change is always that one when the system interacts with the surrounding, then we have what we call enthalpy change. So an enthalpy change can be characterized as an increase or a decrease in enthalpy based on the reaction it has with the surrounding. So it can be that heat will be absorbed from the surrounding, or heat is going to be released into the surrounding. And this enthalpy change is always measured in kilojoules, kilojoules per mole, kilojoules per mole. I'll talk more about this as we continue. So in the last class, I spoke about two different type of reactions. We have exothermic reactions and we have endothermic reactions. So because this system is actually interacting with the surrounding, and it can interact by either absorbing it from the surrounding or losing it to the surrounding. So therefore, that gives rise to whether it's going to be an exothermic reaction or an endothermic reaction. So let's start with exothermic reaction. In this reaction, there's going to be a release of heat energy to the surrounding. The system will release heat to the surrounding. And so therefore, the product will have less energy than the reactant. So when you have the reactant and you have the product. So if the reactant has a certain amount of heat, let's call it H1, then when the whole reaction is done and product is formed, the product will have a certain amount of heat content, which is H2. But we realize that this H2 is less than H1. So therefore, delta H, which is H2 minus H1, is going to be less than 0, meaning delta H is negative. Why? Because during the whole reaction, some heat content have already been put into the surrounding. they have been liberated, they have been released into the surrounding. So therefore, you have less heat content for the product than it was from the what? From the reactant. So that is what we call an exothermic process. But what will happen to the surrounding is that the surrounding will have an increase in temperature. So for an exothermic reaction, because heat has been dished out, heat has been released to the surrounding, it will cause a rise in temperature of the surrounding. So in an exothermic reaction, first of all, the heat content of the product is less than the heat content of the reactant. And simultaneously, the temperature of the surrounding will be increased as well. So that is for exothermic reaction. Examples of exothermic reaction: combustion of fuel. So when you burn fuel, it is an exothermic reaction. That is why temperature will increase. All neutralization reaction, because neutralization reaction of acid and bases, it is always exothermic. That is, heat will be released into the environment, and then we have other other processes as well, like dissolution of calcium chloride in water and all of those things. So you can look for as many examples as possible. Now let's talk about the endo part, endothermic reaction. In this case, it's just similar process, but this time around, you have the reactant as H1 and you have the product, it has H2. What happened here is that the heat content of the product is greater than the heat content of the reactant. Why? Because this system, in the process of performing this reaction, absorbs heat from the environment, from the surrounding. So therefore, delta H, which is enthalpy change, H2 minus H1, will be greater than 0. So meaning delta H is positive. So therefore, this is an endothermic reaction. And what do you think will happen to the temperature of the surrounding like that? What will happen to the temperature of the surrounding? Will it increase or will it decrease? You should put that in the comments. Let's proceed. By the way, if you have not subscribed to this channel, you can see how much content you are enjoying. So just hit that subscribe button and like this video as well. You can also check other videos that I've posted and you will learn a lot. So let's continue. So I've been able to describe these two types of reactions. So examples of endothermic reaction, you have photosynthesis, you have thermal decomposition of limestone, you have dissolution of ammonium chloride in water, electrolysis. So you can also browse as many as much as you can find anyways. So let's talk about the next thing is standard enthalpy changes. Standard enthalpy changes. Let me call that SEC, standard enthalpy changes. So why are we calling it standard? What exactly are we trying to achieve with this name standard? We have what we call standard conditions in what's it called? We have standard conditions in chemistry. By the way, before I forget, if you need the energy profile drawing, you can refer to the previous class to get the energy profile drawing for all this. You can refer to the previous, what's it called? I'm talking about where you have your activated complex, reaction pathway. I've been able to explain all of that in the previous class. So just go and check that video, and then that will be fine. So back to our standard. So we have standard conditions in chemistry. And this standard condition, that is why before you would have heard of the concept STP. It's called standard temperature and pressure. So standard conditions for temperature is 25 degrees Celsius, which is also the same thing as 298 Kelvin. And for pressure, it is 1 atmosphere. Pressure, it is 1 atmosphere. That is 1 atmospheric pressure. So therefore, we can actually have some standard enthalpy change based on some different type of reaction. By the way, we have reactions like formation. We have reactions like formation. We have reactions like combustion. We have reactions like neutralization. We have reactions like solution. So that is something dissolving in one thing or the other. So let me quickly explain like maybe these two. Neutralization is simply acid and base giving salt and water, and solution is when something dissolves in a solute dissolved in a solvent to form a what? To form a solution. So formation, what is formation? Formation is simply when A reacts with B to give C. That's just formation. And then combustion is when A reacts with oxygen to give whatever oxide it is. So oxide of A. Now, The way we define this standard is that there is something we must always pay attention to. For instance, let me talk about combustion now. Do you know that formation of water, it can be regarded to as combustion of oxygen? So combustion of oxygen, let's say H2 plus O2 to give H. Oh no, let me not use oxygen. Let me not use water. Okay, let me use water. I also use something else. So let's say C plus O2 as well to give CO2. I think this will not fit in what I actually want to explain. So let me just stick with that water. So if you want to balance this equation now, you notice that this is going to have 2 at the back here, and this is going to have 2 at the back here. So the equation is balanced now. 4 hydrogen, 2 oxygen, 2 oxygen. So what is now, this is combustion anyway. This is combustion reaction. So if you say heat of combustion, it is the heat released. Okay, I mean standard heat of combustion now. It is the heat that is released when 1 mole of a substance is completely burnt in excess oxygen. It is the heat released when 1 mole of a substance is completely burned in oxygen. So if you want to talk about heat of combustion now, then you cannot have 2 moles of oxygen here. What you're I'm still going to talk about a particular law later that deals with this when we have 2 moles, when we have 3 moles, and all of those things. So this reaction has to be, so you must make this one 1. So you divide everything through by 2. So you have H2 plus half O2 to give H2O, to give H2O. So normally, you know that when we're writing chemical equations, we don't like to use half. Like we always use O number. But when we are defining standard heat, we always, so for instance, if this is going to be standard heat, whatever heat that I'm performing in this experiment, if it's going to be a standard heat, standard enthalpy of combustion, then it has to be that it is 1 mole of hydrogen gas that I'm dealing with. Now, what about formation? Is the heat change when 1 mole of a compound is formed from its element, in their standard state. So, for instance, now this actually also represents, so this H2 plus half O2 to give H2O. It also represents the heat of formation of water. So you can see that how many mole of water do we have here? Just 1 mole of water. So whatever this is now, whatever heat that was involved in this process will also be the heat of formation of water. So that implies that the standard heat of combustion of hydrogen gas is the same as the standard heat of formation of water. So take note of that. Standard. That is under standard condition and all of that. So how do we now measure enthalpy change? How do we measure enthalpy change? So to measure enthalpy change, we have what we call the quantity of heat. So we mostly we determine this thing experimentally, but there are also calculations that we can also do to, you know. So if we have heat energy change, we have Q, which is MC times change in theta. That is change in temperature. I think I should just use T. Yeah. So Q equals what? MC change in theta. The enthalpy change, like I told you earlier, is actually measured in kilojoules per mole. This guy is measured in kilojoules. This is the quantity of heat. But the enthalpy change is calculated using kilojoules per mole. So therefore, it is always Q divided by N, where N is the number of mole that we are dealing with. N is the number of mole that we are dealing with. So C is the specific heat capacity. M is mass. So oftentimes this mass we use it in grams for chemistry. In physics, we mostly use our masses in kilogram. So this is going to be in gram. The specific heat capacity is always measured in joules per gram per Kelvin. Joules per gram per Kelvin. And temperature is measured. Now, I want to quickly call your attention to this change in temperature. You see, change in temperature. Now, let me talk about temperature first. When you're dealing with temperature in chemistry, the standard unit is always Kelvin. Always measure it in Kelvin. But when you're dealing with change in temperature, it does not matter whether you use degrees Celsius or you use Kelvin. You will always end up getting the same result. For change in temperature, you can use degrees Celsius, you can use Kelvin, and you will always get the same result. So that's basically what you need to know about that. Now, let me just give you an example. Will time permit me to give you an example? Um, okay, this is what I would do. I will just go ahead and talk about Hess's law. I will do problem solving in another video entirely. So if you watch this video up to this point and you want me to make that problem solving video, just drop it in the comment. When I receive enough comment, I am going to make that video. But if I don't receive enough comment, that means that I'm not going to make that video. So please, let's continue. So Hess's law. What is this law state? So basically it states that total enthalpy change for a reaction is the same regardless of the route taken, provided that the initial and final conditions are the same. So what this is saying is that if you take a process, let's say you want to produce A plus B to give C. I think I also discussed this in my last class. Oh no, let me say A plus B to produce F. Let me make it far. To produce M. And then you now decide that you don't want to go through this process. You want to say A plus B produce C plus D. Then C plus D, when you get your C plus D, you produce E plus F. Then when you get your E plus F now produce, let's say, K plus U. Then K plus U now produces M. You can see that I've taken this one step thing now. I've taken it to 1, 2, 3, 4. 4 steps now. And all of these now, they have their own delta H. This one has its own delta H. This one has its own delta H. This one has its own delta H. And let's say the delta H of this one is given as this. What Hess's law is basically saying is that it does not matter. Delta H will be the same thing as the sum of all these. So let me just put summation here. Sum of all the delta H, delta H1 plus delta H2 plus delta H3 plus delta H4. So it doesn't matter how long the process that you decide to take, the standard heat will still always remain the same. So that's basically what it is. Total enthalpy change for a reaction will always be the same, no matter what route or the path that you decide to take in a particular reaction. So for instance, when you look at this reaction, carbon reacting with oxygen gas to form CO2. So the enthalpy change for this process, because it's an exothermic reaction, is negative 39 kilojoules per mole. But if you decide to look at another reaction, this one goes like this. You have CO plus half O2. This guy gives CO2. Now, the heat of formation of this guy is negative 283 kilojoules per mole. Then, if you have to find the delta H for this reaction, so the reaction of C plus half O2 to give CO. So how do we now find the heat of reaction for this guy now? So if carbon bonds in this one and form carbon monoxide, what will be the enthalpy of this? So let's call this one delta H1, let's call this one delta H2. See, when you see reactions like this, all you have to do is that you just have to look at what they have in common. And then you have to look for a way to sandwich them actually. So how can you sandwich these guys such that they will be able to give the desired result? So looking at the first reaction, you have carbon and you have oxygen gas. It produces CO2. The second reaction, you have carbon monoxide reacting with what? Being combusted in oxygen to give what? To give CO2. So now we want to get the heat of formation of reaction the heat of the process, the enthalpy change for this particular reaction, carbon plus half oxygen to give CO. So what you need to do is that you have to make sure that you sandwich these two together to mimic this process. So I want to have CO on the right hand side. Since I want to have CO on the right hand side, so this is what I'm going to do. I'm going to flip the second equation. If I flip the second equation, so permit me to just copy the first equation. Let me put it right here. Okay, this is the first equation. Now for the second equation, we have CO plus half O2, and then there's CO2 here. So we are going to have CO2 to give, what is this? CO plus half O2. Then what will happen to the delta H like that? You see, I told you in the previous class, that is why this class is a continuum. If you did not follow a previous class, you might be struggling to understand the new class. That whenever you flip something of this nature, when you flip an exothermic process, it becomes endothermic. So this delta H now will change from negative 283 and become positive 283. I think I should put the plus sign. Positive 283 kilojoules per mole. That is exactly what will happen because now you have reversed the process. Now, if you add these two equations together, this is what you're going to get. So you realize that C does not have any counterpart, so C will still remain itself. Plus, now there's oxygen here, there's also oxygen here. They cannot be in those two places. They have to be in one place. But because they are not of the same number of moles, therefore they will not cancel out. It will only belong to the side with the higher one. You just have to subtract them. So there's 1 mole of oxygen here, there's half mole of oxygen here. 1 minus half is half. So therefore you have half of oxygen here. Then you now have CO2 here, CO2 here. They are of the same mole, they are of whatever, so it cancels out. Nothing goes with CO2. And what do you have finally here? You have CO. So if you look at that now, that's actually giving me this particular reaction. So what do? I then add these two together. So that will be negative 390. So that will be negative 393 plus 283. And that will be, so delta H for this will be negative 110 kilojoules per mole. And you can see that it's still an exothermic reaction. So because you still have what? It being released into the environment. And that is what Hess's law talks about. Then finally, let me talk about bond energy. Bond energy. I said it earlier that reactants, bonds will be broken, and for products, new bonds will be formed. So bond energy is simply the energy that is required to break 1 mole of a particular covalent bond in the gaseous state. So it always involves endothermic, and bond formation always involves exothermic reaction. So when bond is breaking, it is endothermic in nature, and when bond is forming, it's always exothermic in nature. So that is why the enthalpy change, delta H, is always given as summation of all the broken bonds. So bonds broken, that is the heat required to break all these bonds, minus summation of those of the ones that are formed. So bonds formed. So take note of that. When you're breaking bond, it involves endothermic reaction. When you're forming bond, it involves exothermic reaction. So that's basically what it is about. So if you release more energy now to form new bonds than the amount of energy that you use to break those bonds, then the reaction is overall going to be exothermic. But if it requires more energy to break the bonds than it is released when you are forming new ones, then the reaction is going to be purely what? Endothermic. So you can always put that into perspective. And there are factors that affect the enthalpy of reaction, like the physical state, the temperature and pressure condition. I'm not going to be discussing much about that. And one thing I would have loved to discuss in this class is the Born-Haber cycle. You know, when I was defining bond energy, I said it is the energy required to what? To break 1 mole of a particular covalent bond. So what about when it is electrovalent, when it is ionic bond? Don't these also undergo reaction? Yes, they do undergo reaction. And in this case, we actually talk about the Born-Haber cycle, where we talk about the formation of 1 mole of an ionic gas and all of those things. So, but I'm not going to be discussing that in this video because it will be getting too long already. Just subscribe to my channel. When videos like this drop, you'll always be the first person to have access to them. And that's it for today. I'll see you in the next one.